So for section 4.5, we're going to be looking at the multiplication rule and specifically complements and conditional probabilities. I'm going to do a quick recap, and this is stuff you should have on your previous papers, but I kind of wanted to just culminate it together. A is a probability of a certain event or outcome that it occurs. A with a line over it is that that certain event does not occur. So when I put P of A, we're literally saying what is the probability of event A occurring. P of A with a line over it, P of A naught, is the probability of event A not occurring, also known as the complement of A. We calculate it by doing 1 minus the probability of A. This also means that if probability of A naught is 1 minus the probability of A is 1 minus the probability of A naught. See, the idea is that if they should total to 1, then A naught should be 1 minus the probability of A, and A should be 1 minus the probability of not A. Okay? Really, it all culminates from this. They both total to what? They complete each other, so they total to 1. So I could subtract the A over and get 1 minus probability of A for A naught, or I could subtract the A naught over and get the probability of A is 1 minus probability of A naught. This we've seen also, independent events. Whenever I have the probability of A and B, notice multiple events, and means we're going to multiply. We're going to multiply the probability of A times the probability of B. Sort of. See, if it's dependent, then that second probability gets changed. It gets manipulated, it gets affected by the first one. So if I do the probability of A and B, it's still the probability of A, but now it's probability of B given that A has occurred. This right here basically just implies this given that implies that the probability of B has changed or has been affected by A. And we're going to kind of see how that works in this section. Okay, for both independent or dependent, the or is where we add and subtract the overlap. The overlap is really where the only formulas differ. And then how do I get that B given A? We had a couple formulas for that. That was A and B divided by the probability of A. Notice whatever's the given that. We're given that A goes on the bottom. So if it were A given B, you would still have the A and B on the top, but the B would be on the bottom. We'll see an example of that, okay? But whatever's being given that probability goes on the bottom. That's a good formula to know when I have tables. When I don't have tables, but when I have a table, I like to use the second one, where I just take the counts of A and B and divide it by the count of A, and we'll see an example of that. So none of this should be terribly new, but this last part is kind of new, and we talked about it, I think, in one example, but if I want the probability of at least one thing occurring, that means it would be at 1 or 2 or 3. And notice as I keep saying or, we are taking those probabilities and adding them all the way to the nth, all the way to total, right? So at least 1 means 1, 2, 3 as far as we're going, right? This is not practical, especially if I'm dealing with something with like 100 trials and I want to know what's the probability of at least 1. I don't want to add all the probabilities from 1 to 100. We will actually learn how to do that mathematically in the next chapter, so don't stress out about it, okay? But one other option is going, well, wait a second, isn't at least 1 basically saying, look, if I'm doing 1 or 2 or 3 or 4 or 5 or all the way to the nth trial, the only thing we're leaving out is 0, right? So what if I found out the probability of 0? Wouldn't all of this be what we're trying to find? And so if I do 1 minus the probability of 0, then I'm left with everything else we want. So that's kind of the trick on this, is if they say at least 1, well then find the probability of none and take it away from 1, and that gives you everything else. All right. Let's practice these. So let's start with this. Event A is having a positive test result on a drug test. And of course, this comes right after my students who said that we had joint probabilities. So that now we're going to all be tested on that. Event B, person uses drugs. So if you're getting drug tested and you use drugs, does that mean that the test result always comes back positive? Not always. Generally, but not always. What if you don't use drugs? Does that mean that the test will come back positive? Not always. Okay, so let's see how this works. All right, probability of B given A. All right, now I put the words here, but I want to go ahead and say uses drugs was our B. So not using drugs, I will call that B not. Positive test result, that was A. So a negative test result, I would call that A not. Now, we need to make sure on these tables that we go in and we fill in all the totals. A couple of them are easy, like 134, 866, and that totals to 1,000. 44 and 60 would be 50, 950, and our total still checks out to 1,000. So how would I get the probability of B given A? Well, if I use that first formula, here's what we have. We would say the probability of A and B, so they have to both occur for me to get B given A, divided by the probability of what's given. So what is the probability of A and B? That's a positive test result and the person uses drugs. Well, that would be 44 out of 1,000 people. Divided by, what is the probability of getting a positive test result? That would be the probability of just A. That would be the 134 out of 1,000. This looks terrifying because I have a fraction over a fraction, but some of you noticed that they're both being divided by 1,000. You could literally multiply the top and the bottom of this by 1,000. But the idea is that this ends up just becoming, which is not super easy, so let's go ahead and, what was it, 44 out of 134? .328. This is not the formula I would have used. This is why I said you can look at the counts. See, when I say, if I have a table and I want to do this, I could say, what is the count of A and B? Well, how many ABs were there? 44 over, what's the count of A? How many A's were there? 134. So I can go straight to this 44 out of 134 when I have a table just by using counts. That also makes more sense to me than the formula, and here's why. Because what this is literally saying is, what's the probability that your person used drugs, given that they got a positive test result? So that person got a positive test result, right? Hang them. Well, what's the probability that if they get a positive test result, that they use drugs? Well, that would be the 44 people that got a positive test result and used drugs out of the group I'm looking at. I'm only looking at the positive test results. So this is literally saying, what's the probability of being in this if I'm only looking at the positive test results? 44 out of 134. So there's a 32% chance that if you get a positive test result, you're actually using drugs. That means the other, 77% of the people that get a positive test result don't use drugs. Like, well, this test sucks. Well, this is why a lot of times when if you take a job that requires a drug test, you test it. If it comes back positive, they don't just not hire you. What do? Call you back and say, would you like to take the test again? Because, and I'm just real quick, if the test is only 32% successful the first time, right, what's the probability of it happening again? Well, you could do 0.328 times 0.328, and at that point you're like, it becomes more effective. It's the same thing we do if you do pregnancy tests. The test has some wiggle room, so they say, want more than one test, and that lowers the probability of you getting a false positive or a false negative. So again, what does this mean? I do want to interpret this. What does this mean in the context of the question? We are saying, given that A, right? Given that you have a positive test result, what is the probability a person uses drugs? There is a 32.8% chance or probability of a person using drugs. Given that, a person with a positive test result using drugs. This is the group that we're looking at. and there is a 32.8% chance that if they got a positive test result, they are a drug user. That's why they retest. A lot of times the druggies are like, oh crud, it must have got a positive test result, don't go back. So they kind of filter themselves out, right? Anyway, what if I switched it and said, what's the probability of A given B? And because this is what messes with people. They're like, well, how do you know what goes where? Well, the A and B still goes on the top. Technically, it's B and A. But A and B and B and A are still these same 44 people. Okay? So that would still be the 44 out of 1,000 divided by what goes on the bottom this time. Well, what group am I looking at? That would be the B's, which is 50 out of 1,000. I wouldn't do it this way, remember? I would have just used the counts, 44 out of 50, or 0.88. So I would have just done 44 out of the 50. The first one was 44 out of the 134, because this was the given that. And this was 44 out of 50, because this was the given that. So different ways of kind of thinking about it. So what does this mean again? What does this mean in the context of the question? Well, there's a 88% chance of what? There is an 88% chance that, alright, I'll learn to spell something. Apparently caps lock was fun. Of a person who, what? What was our given that this time? Using drugs. Person who uses drugs. There is an 88% probability of a person who uses drugs to get a, what? Positive test result. That means that there's what? 12% chance that if you're a druggie, you may get a negative test result. You get to keep your job. You want to run that risk? I wouldn't. But these are kind of the probabilities, and so this is how this works. But notice whatever was given that, that's the group that we're looking at, and then the actual B and A and B are the same. We're looking at druggies with a positive test result. That's the top. But the given that tells me what's the probability of whether it being a person with a positive test result or the probability of a person. We're looking at a different group depending on what the given that is. Okay, that's enough of that. Let's look at the this part right here is what we're going to look at next, the at least one. So we're going to look at this next. Container contains 10 blue marbles, 4 red. If you draw out 3 marbles at one time, what's the probability you get at least 1 marble? 1 red marble. Okay. Well, we are drawing out 3 marbles. So we could have 1 red. But that doesn't have to just happen in that order. It could be blue, red, blue, or blue, blue, red. Or we could have, so that's 1 red. We could have 2 reds, which would be red, red, blue, or red, blue, red, or blue, red, red. Or we could have 3 reds, which would be, so when they say at least one of them is red, I have to figure out all of these different probabilities and add them up. Well, what's the probability of getting 1 red? Well, probability of the first one being red would be 4 out of a total 14, a 10 and 4. times, what's the probability the second one's blue? Well, there are 10 blue marbles out of, well, now there's 13 left, times, what's the probability that the next one would be blue? 9 out of, now there's 12. This would be the probability of either of these three things occurring. But to get the total probability, because that could occur three different ways, we'd have to multiply this by 3. What's the probability of 2 red? Well, probability of the first red would be 4 out of 14. Second red would be 3 out of. And the last one to be blue would be 10 out of. That would be the probability of either of these three things occurring. The problem is it could occur three different ways, so we'd have to multiply that by 3. And what's the probability of red, red, red? Well, that would be 4 out of times 3 out of times 2 out of. And that only occurs one way, so it'd be that times 1. So we could multiply all these out, add them, and we'd have our probability. So you're going, what the heck? That's okay. Good news is, this is next chapter. You're like, but it's in the homework now. I understand, but remember, what have we left out? When I listed out all of these possibilities, okay, I've listed out 7 possibilities. There's only one more possibility left. The only thing where you're not getting at least one red marble would be if we got, what's the probability? I know my 0 looks like a heart. What's the probability of getting 0 red? That means all of them are, well, that would just be, how many blues are there? 10 out of 14. Second one being blue would be, and the third one would be, and that can only occur one way. So I like that a lot better. Let's go ahead and do that. Let's do 10 14ths, 9 13ths, and 8 12ths. 10 14ths times 9 13ths times 8 12ths. I know that looks horrible, but 0.32967. Or 0.32 or 330 if you want to round it. This is not our answer though, because they wanted at least red, and this was basically the opposite of that. That was no red. So what can I do? If I want the probability of at least one red, my notes say that this is the complement of that. I can do 1 minus the probability of 0 reds. So 1 minus 0.330 would be 0.67. If you'd like to, multiply all these out times 3, all these out times 3, all these out times 1, and add those three numbers you can, you will get 0.67. We will play with this next chapter. For now, they're wanting you to think about how complement could make your life a little easier sometimes. Try again. Sample of 4 different calculators is randomly selected from a group containing 18 that are defective, 35 are not defective. What is the probability at least one is defective? Alright, I don't want to sit there and do one is, this really means what? 1 is defective, or 2 is defective, or 3 is defective, or all 4 are crappy calculators, right? I don't want to calculate each of these probabilities and add them up. It's easier to say at least one is the same thing as that they're all working. Okay? Can we figure that out? Well, we don't know the probability of none of all of them working, right? You have to figure them out. So what is the probability of 0 defective calculators? None. Okay? That means that, first of all, how many calculators are there? There are 18 and 35, that's 40, 53 calculators. What is the probability that I get one that is not defective. I mean, were there 18 or 35 or not? So the probability of defective is 18 out of the 53. And the probability of not defective is the other 35 out of 53. So what's the probability of 0 being defective? Well, what's the probability that the first calculator is not defective? Well, 35 out of 53. And what's the probability that the second calculator is not defective? Well, I just took one of the calculators, right? This is a given now. This probability has changed now because there are no longer 35 working calculators. Now there's only 30. There are no longer 53 calculators to choose from. I kept the first one. Now there are 52. This is also a conditional probability. It's just a little more of a, I think, a logic approach than using the tables and the formulas. So, times, how many are left? 33 defective, 51. So 35 over 53. Times 34 over, 35 over 53 times 34 over, there we go, 52 times 33 over 51. 0.279. So that is not our answer. That's the probability of all the calculators working. We wanted the probability of at least one is not working, right? So that would be 1 minus 0.279. So how about, just double checking my work there. So how about 0.721? One more. Blood testing procedure. Blood samples from 6 people are combined into one mixture. That's really gross. Mixture will only test negative if all the individual samples are negative. If the probability that an individual sample tests positive is 0.12, what is the probability the mixture will test positive? What is the probability the mixture will test positive? When will it test positive? If at least 1 out of the 6, right, comes in positive, the whole batch is considered positive. Okay? How do I calculate that? I don't want to calculate the probability of 1 or 2 or 3 or 4 and all that mess and then add them all separately. I can. We will talk about that a little bit next chapter. Then we'll learn an easier way. But for now, this is the same thing as, what's just the probability of nothing? What's the probability of none of them having this really gross, illness or whatever it is, right? So we know that the probability of, what are we calling it? Negative. Oh, positive. Okay. So the probability of positive is 0.12. And what is the probability of negative then? Also known as not positive. If you want to put positive not, you can. It's weird. So that would be 0.88. Okay? So we're saying we want to know the probability that the test will be positive, which is at least 1, which means I need to find the probability that they're all negative. The probability that we have three negative results. Okay? What's the probability that the first one's negative? What's the probability the second one's negative? And you're like, wait a second, last time that changed. We talked about this in the last section, right? If we're dealing with a huge population of people, these probabilities, they change so insignificantly that we just leave them the same. The previous example, we were dealing with events that were, what's the word for it? dependent, because notice the probability changed as we go. In example 4, we have a large enough population that pulling one person out of it doesn't change the overall probability, so we're dealing with independence, where the probability can just be multiplied, no need to change it. So that's just what? 0.88, 0.88, 0.88. Hopefully somebody did 0.88 to the third. Of course, I can't find the caret on my keyboard. There it is. Either way, I get 0.68147, so how about 0.681? Whew. That is not our answer. That is the probability of no defective. They wanted the probability of at least one positive result, right? That would be this probability. 0.319. We'll play with more of this as we get to the quiz and activities, so focus on that. We're coming up to the test here pretty quick, but I'm giving you time to process it, so work it out.